So, do you know what work is?
What work is?
Yes. Do you know what work is?
Do I know what work is?
Yes.
The actual definition or just like society kind of thing?
Here's a question, okay?
Yeah.
Do you know what work is?
Work it physically?
So just tell me anything. What do you think when I say work?
Kinetic and potential energy.
But like work, you don't think of like...
Working out, exercise.
Okay. Okay, what is it?
Work?
Yes.
It's applied effort
Okay,
to a certain end.
do you know the formula for work?
Not off the top of my head, no.
Is energy times time, or energy divided by time, or something like that.
All right. Work equals force times distance. Basically, in physics terms, this means, well, the amount of force that we apply over a certain distance. Let's say that I push this tree. Well, as hard as I push, it's not moving. I've applied a force, definitely, but when distance is 0, work is also 0. I don't do any work. There's one other way we can also define work, and that is as the change in energy. Well, I certainly can't move this tree, but I can move the stick. Let's say that the stick is moving at a slow rate, but then I apply a force to move it faster. It's that change in kinetic energy that is also work.
Miles, do you even know what kinetic energy is, dude? Here, Miles, and everyone else watching, let me explain to you what kinetic energy is. So kinetic energy is the energy of motion. What does that mean, Jersey? Well, we can use it and to find how much energy we have while we're moving. And how do we find it? Well, there's this very neat formula. It's kinetic energy is equal to 1/2 mv squared. And what are all those terms? Well, 1/2 is just normal, but you would expect 0.5. Then m is your mass. You could use whatever units you want, but we usually use kilograms. What about v? Well, v is your velocity. Velocity is usually measured in meters per second. But what is else? There's nothing else, right? Well, no. You see, because kinetic energy is the energy of motion, we square the velocity. So let me give you an example. Me and Miles both want to run. So me and Miles both weigh about the same. So both me and Miles are about the same weight. But Miles wants to carry some 10-pound weights, one in each hand. So Miles's mass is going to be a little different than mine. But we both run the same speed. What does that mean? That means Miles is going to have a little more kinetic energy because he is carrying more mass. Remember the formula, 1/2 mv squared. The more mass, the more kinetic energy. It's a direct proportion. The more mass, the more kinetic energy. Same with velocity. The more velocity, the more kinetic energy. That means if I want to get the same kinetic energy as Miles but don't want to carry weights, I could just run a little faster. That would give us both the same kinetic energy.
Alright, now you know what kinetic energy is. But there's another type of energy as well.
Oh my god, Miles. I'm so sorry. That's just potential energy at work. Here, I'll come show you what it is. Follow me, dude. Alright.
Alright, I'm not sure where Jersey went, but let's just hope he's doing some work. Alright, I'm up a tree and I'm here to tell you a little bit more about potential energy. Now, there are a few different types of potential energy, most notably spring potential and then also gravitational potential. I'll show you a little bit about gravitational. Alright, here's the formula. Gravitational potential equals mgh. M is the mass, g is gravity, which is a constant 9.8, and then h is the height that you drop it from. I have two weights to demonstrate. Both will be dropped from the same height. Let's start with the 5-pound weight. Now let's go to the 10-pound weight. Same height, of course. Now you can see that both were dropped from the same height, but I would still say that their gravitational potentials were different, and this is because their masses were different. So hopefully that explains a little bit more about the relationship between all the variables in gravitational potential. Well, now I'm off to find where Jersey is.
So Miles was right. I was doing work. Actually, I wasn't just doing work. I was also experiencing power with this lawnmower. So Miles already told you what work is. Work is equal to force times distance. And we could figure out both of those variables really quickly. Force is equal to ma because of Newton's second law. So we can figure out the force by using F equals ma. And so we can calculate the mass of the lawnmower and then its acceleration. That way we get its F. Now, B is not that hard either. As you could see, I was mowing in lines back and forth. And so if we figure out the distance of one of those lines and just multiply it by the amount of lines I did, you can figure out the distance if we ignore the circles in the back, but that doesn't really matter. Now, that distance times the force that the lawnmower is using in newtons will give us our work in joules. Now, that's not it. If we divide our work over our time, so work over time, that is going to equal our power, because power is equal to force times distance over time. But that's not it. What is distance over time? What is that? You said velocity? Well, you're right. So if we find the force of this lawnmower and the velocity that we're going at, we can figure out the power that we're using. Now, there's one more thing we didn't tell you. Energy is always conserved within a system. So let's go back to the tree and we'll go show you an example of conservation of energy. I'll see you. So here we are, we're back on the tree. So now I'm going to be explaining the law of conservation of energy to you. So we're going to start off with this 5-pound weight, okay? So what's going to happen with this 5-pound weight is I'm going to drop it. So right now, currently the 5-pound weight has a current potential energy. We could calculate that using mgh is equal to potential gravitational energy. So when I drop it, what's going to happen? Well, it's going to start to lose some of its gravitational potential energy and turn into some kinetic energy. So let's do it. Now, at the bottom of the ground, that weight has 0 potential energy and 0 kinetic energy. But at the instant before it hits the ground, it will have the maximum kinetic energy and the least potential gravitational energy. But let's use a different weight. If we use a 10-pound weight, the system is a little different because there's more mass in this one, so there's more potential gravitational energy. So when I drop it, they will reach in the same time, but the amount of gravitational potential energy that weight has will be more.